Imagine you're buying a house. Every day, we make predictions using patterns from the past. Machine learning tries to automate this process. If we plot the data from the housing data set, where we have living area of each house and the corresponding price, then each point represents a house and its price. Larger houses usually cost more money. The data already contains a hidden pattern. Our goal is to teach a machine to discover that pattern. Suppose a new house appears. The machine has never seen this exact house before, but it can use past examples to estimate the price. Using past examples, the machine learns a pattern. This process is called supervised learning because the machine learns from labeled examples. Input data goes in, predictions come out. Because price is continuous, this is called regression. Regression predicts numerical values like prices, temperatures, salaries, or stock values. But how does a machine find the best line? And that question leads us to the core of linear regression. Our dataset already contains a hidden trend. As house size increases, price also tends to increase. But this relationship is not perfectly exact. We need a line that captures the overall pattern. Some lines are terrible predictors. This line barely follows the trend in the data. This one is too steep and overestimates many prices. So, how do we find the best possible line? Linear regression finds the line that best fits the data. This line follows the overall direction of the dataset. It may not pass through every point, but it minimizes the overall prediction error. The simplest mathematical form of a line is y equals mx plus b. The slope controls how steep the line is. The intercept controls where the line starts. Together, these values define the prediction line. In machine learning, we usually write the equation like this. This is called the hypothesis function. It represents the model's prediction for a given input. Now we need a way to measure how good this line really is. But how do we know if a line is good or bad? To answer that, we need something called a cost function. The prediction line depends on parameters. Parameters are simply numbers that control the model. By changing these values, the prediction changes too. Theta 0 and theta 1 control the line. Theta 0 decides where the line begins. Theta 1 controls how steep the line becomes. Changing theta 1 rotates the line. A small slope creates a flatter line. Increasing the slope makes the line steeper. Even a small parameter change can drastically affect predictions. Changing theta 0 moves the line up or down. The overall slope stays the same, but the entire line shifts vertically. Together, slope and intercept define the final prediction line. Real problems usually have multiple features. House price may depend on many different factors: size, bedrooms, location, age, and many other variables. Machine learning models combine all these features together. This compact form is heavily used in machine learning. As models become larger, compact notations become extremely useful. This notation allows machine learning systems to scale efficiently. Now we can represent predictions mathematically. But how do we measure prediction error? To improve predictions, we first need to measure how wrong they are. How does a machine know whether a prediction is good or bad? To improve predictions, we first need a way to measure mistakes. That measurement is called the cost function. Suppose our model predicts prices using a line. Some predictions will be close to the actual values. Others may be far away from the real answer. So, how do we measure how wrong this line really is? Some predictions are accurate, others are not. The vertical distance represents the prediction error. Smaller errors mean better predictions. Our goal is to make all these errors as small as possible. We square the errors so negative and positive values don't cancel out. Large mistakes become much more expensive after squaring. This strongly penalizes very bad predictions. Now we can combine all the errors into a single number. The cost function measures how bad our predictions are. A large cost means the model is making large mistakes. A smaller cost means the predictions are improving. Machine learning is essentially an optimization problem. The machine keeps adjusting parameters to reduce the cost. So, how do we minimize the cost? To do that, we need one of the most important algorithms in machine learning. Now, we need a way to reduce the cost function. This is where optimization enters machine learning. The goal is to slowly move toward better predictions. Imagine standing on a mountain in thick fog. You cannot see the bottom, but you can move downhill step by step. Each step brings you closer to the minimum point. Gradient descent works in a very similar way. Gradient descent repeatedly updates the parameters. The model checks which direction increases the error. Then it moves in the opposite direction to reduce the cost. This process repeats thousands or even millions of times. The learning rate controls the size of each step. Small learning rates are stable but require more time. Large learning rates move faster but become unstable. Choosing the right learning rate is extremely important. After every update, the predictions improve. At first, the model may fit the data very poorly, but each update pushes the line closer to the optimal solution. This gradual improvement is how machine learning models train, but there is more than one way to perform gradient descent. Different training strategies can dramatically affect learning speed. There are multiple ways to perform gradient descent. Different training strategies can dramatically affect performance. Some methods are stable, others are faster. Batch gradient descent processes the entire dataset before updating. The algorithm first examines every training example. Only after processing everything does it update the model. This approach is stable but can become slow for massive datasets. Stochastic gradient descent updates after every training example. Instead of waiting for the full dataset, the model learns continuously after each example. This makes learning much faster but also noisier. Each method has different strengths and weaknesses. There is no perfect method for every situation. Engineers choose training methods based on scale, speed, and stability. Deep learning systems train using optimized stochastic methods. Modern neural networks contain millions or even billions of parameters, yet they still rely on the same core optimization idea. Gradient descent remains one of the foundations of modern AI, and this is the foundation of modern machine learning. From linear regression to deep learning, the same principles still apply. Let's connect everything we learned. What started as a simple line became a complete learning system, and those same ideas still power modern AI today. This entire process allows a machine to learn from data. First, the model observes examples from the real world. Then it makes predictions and measures its mistakes. Finally, gradient descent slowly improves the predictions. At its core, linear regression is simply pattern recognition. The model tries to capture relationships hidden inside data. That simple idea eventually evolved into modern artificial intelligence. Linear regression may look simple, but the idea is extremely powerful. Modern AI systems are built on these same optimization principles. Modern neural networks contain millions or even billions of parameters, yet they still learn using the same fundamental concepts. Predictions are made, errors are measured, parameters are updated. Gradient descent remains one of the core engines behind AI training. Linear regression is often the very first machine learning algorithms people learn. Find patterns, reduce error, improve predictions. And everything starts with a single line.